The Doppler log is one of the more common and popular modern logs, which uses the Doppler principle to measure the ship's speed. It uses the sound energy as a signal, and it is claimed to be more accurate than the other logs such as the EM log, because in shallow water it can measure speed over the ground as well, which is not the case with EM logs. EM logs can, or electromagnetic logs, can only measure speed through water, whereas Doppler logs can measure speed through water as well as over ground. Alright, so before we start studying the principle of Doppler log, let me just explain the concept of the Doppler effect. The effect of the Doppler principle is shown on your screens here, where you can see that the pitch or note of the whistle of a train, for example, which is coming towards you, is higher than when the train or the whistle is going away from you. As the train passes you, the whistle note drops from higher to lower, and the note is heard by the listener is higher than transmitted from an approaching sound source, and it is lower than transmitted from a receding sound source. So let me show you an example here. For example, I'll play the jet sound as well as the siren sound, and you can see, and you have to observe and listen carefully to the change in the frequencies when the source of the sound is approaching you and when it is going away from you. Alright, so let's see. So this is basically the Doppler effect, that when the source of the sound is approaching you, the frequency increases and reaches you, it is maximum, and when it is going away from you, then it starts to decrease again. Alright, so the same effect is heard with fire engines and ambulance sirens, so on and so forth. So if pitch or the frequency of the signal is graphed against time, you can see this is how the curve will look like. So the difference between the frequency heard or measured by the listener and the frequency transmitted by the source is an indication of the speed of the sound source. So in other words, frequency difference depends on the speed at which the source of the sound is traveling. Now this is the Doppler effect, and the difference between the frequencies is known as the Doppler shift. So because if you measure the frequency difference accurately, then the speed of the source of the sound, or in our case the speed of the vessel, can be found. Let me show you how it is done. Alright, so the Doppler log principle is applied to the ship's log in the following way. A beam of acoustic energy is transmitted from the ship at a certain frequency. Now if you don't know what acoustic energy is, acoustic energy or acoustic wave is the same as a sound energy or sound wave. Alright, it is just another word for it. So once you transmit the sound energy from the ship at a certain frequency, the energy is reflected from the seabed or the water layer in the case of speed measured from the water, speed measured through the water, and returns to the ship when it is detected, and its frequency is measured for comparison with the transmitted frequency. So the received frequency when the sound energy reflects off the seabed is compared with the transmitted frequency. The difference in the transmitted and received frequency is, of course, as we studied before, is the Doppler shift, but it also gives us an indication of the speed of the vessel in this case. Alright, so when comparing both the transmitted and the received frequency, you can see that if the frequency received is equal to the frequency transmitted, if they are the same, that would indicate that the ship is stopped. However, if the received frequency is more than the transmitted frequency, that would mean that the ship is moving ahead. Finally, if the transmitted frequency is more than the received frequency, that would mean that the ship is moving astern. Now you can see here how I am displaying that the ship is stopped. So imagine there is a ship being, say, at anchorage, and the ship tries to use the Doppler log. It sends the frequency transmitted That frequency hits the seabed and is reflected off, and this is the frequency received. So in this case you can see that the frequency transmitted equaled the frequency received, which would mean that the ship is stopped. In the second case, where the ship may be moving ahead, you will see that the frequency received will be greater than the frequency transmitted. So the red beams are the frequency transmitted and the blue is the frequency received, and you can see that when the ship is moving ahead, the frequency received will be more than the frequency transmitted. In the third case, you will see that the transmitted frequency is larger than the received frequency, which in this case would mean that the ship is moving astern. So in Doppler log configuration, one of the popular configuration used is the Janus configuration. In Janus configuration, we have two beams that are used. One beam which points forward and one beam that is pointing aft. This is done to eliminate some of the errors which exist with this log due to the pitching of the vessel. This is known as the Janus configuration because it is named after a Greek god called Janus, who could see the future and see the past. I think the god had two heads, one looking forward and one looking past, and that is why the Janus configuration is named after the same Greek god, because here also you have two beams, one beam looking forward and the other beam looking aft. The angle of the beam is about 60 degrees to the horizontal. It is not directly perpendicular. The reason for that is that if the configuration or if the beam was less than 600 degrees, or let's start with less than 600 degrees or more than 600 degrees in the first case, you can see then too little reflected energy is returned back to the receiver. Alright, if it was more than 60 degrees, then we have an insufficient angle to obtain a reliable speed reading. So in the first case, if the angle of the beam is less than 60 degrees, so too little reflected energy comes back to the receiver. Most of it will get lost in the sea itself, it will get dissipated. And if it is more than 60 degrees, then the angle will be at insufficient angle to obtain a reliable speed reading. Alright, there will not be a big enough forward component of the beam to get a reliable speed measurement. Then we have another configuration called the cross-track configuration in Doppler log. Now this configuration is very useful and is normally found on ships which are more than 50,000 gross tonnage. This is because this configuration enables sideways or cross-track speed to be measured. In this case, you have two mutually perpendicular Janus configuration arrangements to measure the speed in 2 dimensions. This arrangement is also known as the docking log, and it provides the actual movement indication of the vessel. So the cross-track speed may be permanently shown on an additional digital display, or it may be shown only when the cross-track button is pressed on your Doppler log, depending on the display design. So as you can see here, you have 4 element transducer arrays, fore and aft and port and starboard. So in this case, you can measure both the fore and aft speed as well as the port and starboard speed, which will give you the athwart ship speed movement of the vessel. Cross-track speed is useful as it allows the integration of 2 separate speed vectors to get a much more accurate measurement of the ship's actual movement. So these readings are averaged out to get an idea of the ship's movement. Knowledge of this movement is particularly important and useful in general navigation, especially with sophisticated navigation computers, which control course keeping very accurately to minimize steaming distance, time and fuel. It's also useful for particular navigation as practiced by the surveying vessels, seismic vessels, rig tenders and dynamic position vessels, as well as pilotage, especially when vessel is in strong currents and when berthing large vessels. Alright, so we'll keep going because I just mentioned all this. So then we have 2 operating modes in Doppler log. So the Doppler log is capable of providing both speed through water and speed over ground. This is a distinct advantage that the Doppler log has over the electromagnetic log. Now this is carried out by a single transducer which should be able to switch from one mode to the other. Now in bottom tracking happens in shallow water where the energy is reflected off the seabed and thus the speed measured is over the ground. Hence this is called the bottom track or bottom log system. Then we have the water tracking mode. In this happens in deep water where the bottom is too distant to reflect the sufficient energy. Electronic circuits within the receiver then enable the sound energy reflections from a predetermined water layer to be used to measure the speed. This speed measured is speed through the water, and this mode of operation is called the water track or the water log. If speed measured in bottom track differs from the speed measured in water track during that time, then definitely a current is existing in the system. A current exists at sea. A Doppler log may be able to hold bottom log down to about 200 meters, and it might use a water reference layer at about 20 to 30 meters for water track. The log may operate at a minimum underkeel depth of 2 meters. Thus, for underkeel depths of from 2 to 30 meters, the log must be operating in bottom track using reflections from the bottom. In depths greater than 200 meters, the log must be operating in water track using the 20 to 30 meters reference layer. But for depths between 30 meters and 200 meters, the log can operate either in bottom track or water track. The choice remains with the operator. Like any other instrument, the Doppler log is also prone to certain sources of error. The first one is the transducer alignment. Because the sound energy beams should be exactly fore and aft as also port and starboard. Most of the transducers have an indicating arrow which is to be lined up with the vessel's fore and aft center line at the bottom of the hull. There have been cases where the transducers were fitted in reverse after a stay in dry dock, and as a consequence the forward movement was indicating by a negative number or stern speed and vice versa. Trim will also cause a misalignment of the beam in the vertical plane, but this error is generally small as the integrity monitoring done by using the Janus configuration kind of mitigates the effect. Then we have the ship's motion such as the rolling, pitching and surging and heaving, which all contribute to instantaneous accelerations and therefore change in speeds which the log is measuring. This may then differ from the true forward speed of the ship. For a fore and aft axis log, pitch is the most significant cause of error. For a cross-track log, errors caused by rolling can be significant. You must pay particular attention to the instantaneous motions while relying on the speed shown by the log, and must treat the readings with caution even after averaging them over a period of time. Finally, the speed of the sound varies with water temperature, salinity and pressure. Temperature is the most significant of these factors. The log will read wrongly if the actual values differ from the assumed values of salinity, pressure and temperature. Some Doppler logs may be compensated for errors caused by sea change. The advantages of a Doppler log are that Doppler logs provide reliable and accurate speed readings. They can compute speeds both forward and aft as well as athwartship, and can calculate cross-track speeds as well. They can be used to measure speed through the water as well as speed over ground. However, the distinct disadvantage of a Doppler log is that the officer on watch must pay attention to relative motion calculations if attempting to calculate the vessel's speed or current whilst specially water tracking, like I explained before. In terms of general maintenance, display screens can be regularly dusted and occasionally wiped with a lint-free cloth and purpose-made cleaner if contaminated by finger marks. Planned maintenance should include checks of the flanges for water ingress. In dry dock, you must inspect the window and the surrounding areas. The display unit does not require periodical maintenance since the unit has no movable mechanism Perhaps the analog meter and the magnetic counter. The unit should be kept clean and free from dust and the connections checked for tightness from time to time. Check the window and the surrounding of the transducer sensor when the ship is in dry dock. Check periodically for leakage of water at the flange and the gasket of the transducer assembly. Remove any marine growth from the transducer or sensor assembly. Most transducers are of suitable surface, not needing any coating. But some of the older ones, you may clean and paint surface of the transducer with anti-fouling paint as to a suggested thickness as advised in the manufacturer's instructions. Do not touch the adjustable electrical parts inside the unit, which is best left to an electrical officer on board or a qualified service technician. It is possible to correct a fixed error caused by misalignment of the transducer at installation by adjusting the controls inside the unit. But since this system indicates a so-called water speed originally, check the error caused by the current of the tide. In terms of accuracy, devices measuring speed and distance over the ground should meet the performance standards in waters of depth greater than 2 meters beneath the keel. Speed information may be presented in either analog or digital form. Where a digital display is used, its incremental steps should not exceed 0.1 of a knot. Analog displays should be graduated at least every 0.5 knot and be marked with figures of at least every 5 knots. Errors in the measured and indicated speed when the ship is operating free from shallow water effect and from the effects of wind, sea bottom type, current and tide should not exceed, for a digital display, 2% of the speed of the ship or 0.2 knots, whichever is greater. For an analog display, 2.5% of the speed of the ship or 0.25 knots, whichever is greater. And for output data transmission, 2% of the speed of the ship or 0.2 knots, whichever is greater. The performance of the equipment should be such that it will meet the requirements of these standards when the ship is rolling up to 10 degrees plus minus and pitching up to 5 degrees. Finally, we discuss the sighting of the logs and how they cause potential errors. So generally speed logs are very reliable, but you must understand the speed measurement errors can arise and under what circumstances the log is likely to be inaccurate. These cases is especially important for electromagnetic logs, where the measurement of the speed depends on the flow of the water across it. So these logs and this section here, potential causes of errors, reference to the electromagnetic logs in particular, not so much to the Doppler log, because the Doppler log does not depend on the flow of the water across the transducer. Alright, so here we talk about the potential causes of errors that are caused due to the flow of the water across the transducer. This occurs especially in electromagnetic logs. So let's start with the first one. Distortion of the water flow passing the hull because of the hull shape or the potential flow field in case of an electromagnetic transducer. Positioning of the sensor then becomes very important. The flow pattern may change with draft, speed and trim, and errors thus may be variable. So as you can see here, if the flow of the water across the transducer gets affected, the speed measurement through the water in case of the electromagnetic log will also get affected. In the second case, the viscosity of the water results in water being carried along with the hull by friction. This is called the boundary layer effect. The boundary layer may be a few centimeters at the bow of a ship, but more than a meter at the stern of the ship. Some logs may have to extend beyond the boundary layer to ensure the sensor is in clear water. They may then have to be retractable to avoid damage. In the third case, we have the disturbed water flow around appendages of the ships, such as bilge keels, anode plates, plate edges, etc. Again, because of these appendages, if water flow gets affected, then the electromagnetic log will not be able to read the speed of the water accurately. In shallow water, the changes the water flow around the hull, particularly the under keel, because it also affects the actual speed of the ship over the ground. Thus, the speed indicated by the log may be only approximate in shallow water. Now, how does this happen? Because in shallow waters, as the vessel speeds through the shallow water, the flow of the water beneath the keel also speeds up. In such case, due to Venturi effect, there is a suction that occurs under the keel of the ship. Due to this suction, the ship kind of sinks towards the bottom. This is called squat. Now, because of this sinking, the water flowing beneath the keel of the ship also speeds up, and this results in the EM log or electromagnetic log to think that the speed of the water is more than what it actually is. Then we have the average motion errors. The first one is the oscillatory error, where instantaneous readings may be in error when pitching, rolling, heaving, and surging. In pitching, for example, the log sensor is mounted well below the pitching center and probably well forward or well aft of it. The pendulum effect means considerable linear acceleration of the sensor, causing errors which can be significant. The log is designed to measure speed along the track or the axis, the course, and in the horizontal plane. If the ship's attitude deviates from these, then a speed error is introduced. So any kind of trimming, pitching, and yawing causes this error, but the effects are usually small. Leeway errors can also be significant. Then we have the maneuvering errors, which may be significant, for example in the input to an ARPA or radar during a high-speed turn in a close quarter situation. So when you start turning the vessel at a high speed, the flow of the water across the transducer of the EM log also gets affected. In that case, you should wait for the vessel to go on a steady course, settle down on this new course, and then get the speed reading. And finally, we have water mass movement, where the speed of the ship measured gets affected by the factors of the currents, tidal streams. Now, not all logs are affected by all of these factors, and in calm seas in deep water with no current or wind, the log will generally give results which are accurate enough for general navigation. However, if there is a strong current that exists, some of this may get affected. I have talked about the performance standards before, so I will not repeat this again, and I'll keep going. Finally, we talk about the future considerations of the log. Now, since the last few years, and due to the advent of cheap and effective computing processing power, a new type of log has been trialed, which actually does not fall either into the category of the electromagnetic log or the Doppler log. Now, these are called as electronic acoustic logs, as there are few processors with memory and the usual modern computing circuitry to estimate the speed through the water as well as speed over ground. These work on acoustic modulation principle, where the sound echo is received by two transducers specifically placed at a known 4.5 distance, and the phase of the echo wave difference is used for speed estimation. The speed is estimated from the fixed distance between sensor elements divided by the estimated time delay from acoustic correlation, where two signals are compared by shifting one relative to the other in time and choosing the time shift where the best match is found. Somewhat similar method is used by the GPS receiver to get the time difference between the code received of a satellite and its replica in the receiver system memory. These electronic acoustic logs are capable of giving both speed through water and speed over ground, as they do not rely on the passage of water past a sensor but rather on the reception of the echo. So I hope this video was useful for you to understand what are Doppler logs and what are the factors, especially with the sighting of the logs, that affects the speed measurement, particularly in electromagnetic logs. Let me know what you thought about this video in the comment section. I'll see you soon with my next video. Bye guys.